Good morning. Welcome to Krishna's class. We were in the process of introducing a general version of the Vitali convergence theorem. We worked out the preliminaries, and last we did was defining the concept of tightness. Okay. Then we looked at a couple of examples also, and we have two examples in particular. The first one was you have E equal to the unbounded interval 0 to infinity, which is not a set of finite measure. Then we had En defined as the subintervals n plus 1 etc. Then we defined the class of functions. Then we had defined the class of functions Fn, the characteristic function of En for n equal to okay. Now in this case, because that Fn converges to F, which is identically 0 on point X. Then we also, it's easy to see that the convergence and the integration cannot be interchanged. So we observe that limit n tending to infinity integral this is equal to 1, which is not equal to so the interchange of integration and the limiting process is not valid. Okay. A second example that is closely related to this is the following. We have once again E as 0 to infinity, and we have En in this case equal to n plus 1 by n. For n equal to 1, 2. Then we defined once again Fn as before, characteristic function of and it's quite easy to see that Fn which is identically 0. That's because, see, this is what you have. Suppose this is 0, this is 0, 1, 2, etc. So what you have is this. This is your E1. This is your E1. And E2 is this is 3 by 2, and so on. And eventually you have what you call N to N plus 1 by 2. Therefore, the measure of these subintervals shrink to 0. It has length equal to 1 by n, and you are taking the characteristic function of this. And it's quite easy to see that this goes to 0. I mean, that is as before. But now what you have is that if you investigate this, see, limit n tending to infinity, integral over e fn equal to limit n tending to infinity 1 by n, which is equal to 0, which is equal to integral over f. So you have equality here. So here the interchange of limiting process and the integration is valid. So whereas in the previous case, integral does not compute. So these are the two examples which are very easy to, of the same type, but this happens. Now that shows that, see, these two classes of functions have the same behavior, same sort of behavior, except for the fact that ens shrink to 0. Or consequently, the integral of fn's go to 0. Now this is what this is the difference between these two. Okay. So once again, you see that the commutativity of integral with the limit holds in some cases even when the measure of E is not finite. Okay. Therefore, what does it say? It says that possibly some extra conditions other than uniform integrability of the sequence would assure you that the commutativity of integral and the limit. I mean, this is the Vitali convergence theorem, where we assumed that measure of E is finite. In that case, we proved that if the Fn converges what you call Fn is uniformly integrable, then the interchange of limiting process and the integration holds. Okay. But the moment we changed it to a measurable set which is not integrable, which is not finite, then which is not having finite measure, then we found that in general this theorem is no more valid. So with some additional conditions we have. And in this context, we observed one fact. Okay. Under these conditions, the fn's that we have chosen in the second example, you see, the integral of that outside a set of finite measure can be made as small as you please. Okay, so observe. that even epsilon there exists a finite measure such that integral of less than c. So the tail of the integral can be made arbitrarily small. Now, in the second case, what we have is the choice is simple. To choose E naught to be see, you have this 1 by n going to 0. Therefore, by choosing n sufficiently large, you can make this as small as it is. This is what we are doing. So, you take the interval. So, given this exists. Okay. Now choose zero to n. Then what happens? Then one observes that over E naught E slash E naught Fn is less than okay. So that is one property. This is not there. Satisfied by in example 1. The reason is this. You see, no matter how large n you choose, capital N you choose, and define E naught as this. Now you see that the integral of this is going to be equal to 1 for n sufficiently large. So it cannot be made arbitrarily small. Okay, that's the reason. Because you see that this is the reason. Integral n to infinity. This is the reason. So possibly, if we put a restriction of this kind on the class of functions that we have, then the theorem will be, maybe we are able to push the proof of the theorem across and get the general version of the Vitali convergence theorem. That's the whole idea. Okay. Now, it is in this context that we introduce the concept of tightness in this context. So what did tightness say? We said that if f is a family of measurable functions on E may not be of finite measure, then f is said to be tight over E if given epsilon there exists a subset E naught of finite measure such that integral over is less than epsilon now this is the tightness criteria, and you can see that example 1 Fn is not tight. Whereas in example 2 okay, therefore possibly if you assume this tightness we may be able to prove the Vitali's convergence theorem. Okay, so you don't have a free passage to the general case. Some additional assumptions are to be made. That's what it is. Okay, so Let's make some remark. Okay. So we if f is a family of measurable functions on E, not necessarily finite measure, that is uniformly integrable and tight, uniformly integrable and tight over E, then each so we shall try to prove this. Give a proof for this. F tight over implies there exists E naught E measurable and measure of finite such that integral over E slash E naught of mod f less than epsilon for every f belonging to this type. So now what we do is we choose a particular value for epsilon. Then let E naught the set of finite measure in contained in such that for every f by tightness such an E naught exists. So this is what you have. What you call a Venn diagram will be is this. This is E naught, mu E naught or m E naught is finite, and me may be finite or infinite. Okay, we are interested in this. Now f is uniformly integrable over E, which implies E naught. Therefore, epsilon equal to 1. There exists a delta naught positive such that for every A contained in E naught, measure of delta naught integral over A Okay. Now this is the consequence of what you call uniform integrability. Now what you do is, so you can write E naught as a finite union of AI. Because E naught is a finite measure, therefore you can do this such that AI intersection AJ is empty for I not equal to J. And measure of AI is less than that. This is possible. That's a simple consequence of this. Therefore, what you get? Now, what we want is we want to prove the integrability over the years. That's quite simple. You proceed as you have this. Therefore, what you get? Integral over E naught mod f is equal to integral over union AI one to n if this uses just additivity over disjoint measurable sets, and of course linearity of the integral. And this, of course, each one of this is, since measure of AI is less than delta, you see that mod f or integral over AI of mod f is less than 1. Therefore, this is less than. Therefore, what you have, hence, integral over E naught which is less than, therefore the result false. Okay, so all the f's are integrable. Okay, so uniform integrability with tightness on even sets of not necessarily a finite measure have the integrability. Now we are in a position to give the statement of the general intent. Again, the basic question that you address in the Vitali convergence theorem is the interchange of integration and limiting. So let us state the theorem. Let sequence of functions on E on a measurable set E need not be of finite measure which is uniformly integrable and tight the assumption that we are making. Suppose F pointwise almost everywhere on E, then over E and limit that is interchange of limiting process and integration is valid. You put the additional condition that Fn is right over. Okay. So let us prove this here. We have got a feeling now for the problem. Now we will prove this theorem. The proof is very simple. Obvious way, you for a given epsilon positive, you cut out, you identify a subset of finite measure. So that on the complement of that, the integral of each Fn is less than epsilon or epsilon by 2 or epsilon by 4 or whatever you prescribe, small. Okay. So we are now not bothered about this, and from there you can conclude that the limiting function also satisfies the same condition on that part. And on E naught, where you see that the sequence of functions is uniformly integrable, and using that, since the measure of E naught is finite, you can use the standard Vitali's theorem on. Okay, and now combine the two results, and then you get come to the conclusion. Okay, let us look at this. So let by tightness there exists a measurable subset E naught contains with measure of finite such that integral over for every. So that comes from the tightness. Okay. Now using Fatros lemma, you apply on this, and to get to the function f, what you do is Fn converges pointwise almost everywhere on. Therefore, you have pointwise we have which is less than epsilon y. So the integrability of f on the on the complement of E naught is now assured. So this is a nice conclusion. Okay. So f is integrable. That's a conclusion. Now what we do, see, we want to see our objective is this eventually. What we want to do is we want to show that integral Fn minus integral over F can be made arbitrarily small by choosing n sufficiently large. By choosing n sufficiently large. Which in turn tells that this integral, the limit of so that limit n tending to infinity of this is our objective. So this is the important part. See, we want to prove this part. This is our main result that we want to prove. So how do we do that? Okay, so let us estimate this. So integral over E slash E naught. That means we are estimating on the tail, on the portion that has been chopped off. Okay, this is less than or equal to integral over slash E naught and this is so this is so we have estimated this integral on the tail of it. So what is remaining? E naught is a set of finite measure. There you can apply Vitali convergence theorem. Okay, so E naught is a and all conditions of Vitali's theorem are valid, satisfied on. Therefore, we can immediately read out the conclusion of this. Therefore, f is integrable over E naught is E naught, and we can choose an n, can choose an n such that this is less than so it's for the same epsilon that we are working on this, and therefore f is integrable why it is so, because integral over of and which implies which is less than and the consequence is that, so this implies what? The consequence is that is interchange of integration and limiting process So this is now what? So that is the general Vitali theorem, and the general Vitali theorem has an additional condition of tightness when the measure of the domain is infinite. So it doesn't, our examples demonstrate that if you do not have that, such a condition, it will not work. Okay, now we give a corollary is analogous to the corollary that we proved earlier, and here it shows the the sort of, this is a inevitable sort of condition. Okay, so what we prove is that corollary which shows the inevitability of the uniform integrability and the inevitability of conditions. So the proof of this theorem is an improvisation of the proof of the corresponding theorem. So let Hn be a sequence of non-negative integrable functions on now E is not assumed to be finite. Suppose if Fn or Chen converges to 0 for almost then limit n tending to if and only if uniform integrable and tight on Now only one part is to be proved here. The other part follows. If we assume Hn is uniformly integrable and tight, then this interchange of limit and integration follows immediately. Now what you have to do is now improvise a proof analogous to what we did in the restricted version of the Vitali convergence theorem. There was a similar result available there. The additional fact that comes is the tightness. So tightness also has to be brought into the picture for proving this theorem. I think I leave that to you. It's not difficult. One can take it as a good exercise. Okay. So I think I'll conclude today's lecture with this corollary, and we'll go and take up what is called the concept of convergence in measure in our next. Okay, thank you very much.